All right, so section 11.5, alternating series, what we're going to look at in there is positive terms that all of a sudden start alternating signs. So what we're going to do is we're just going to remove the -1 and look at just, they call b sub n. I like to use that because it's going to be the basic part of the function without the alternating signs. So the first thing we want to do is we want to do the limit as n approaches infinity of b sub n equals 0, because if this doesn't equal 0, then it automatically diverges via your divergence test. And then second, we'll prove that it is a decreasing sequence, and therefore for all your n, therefore it's going to converge. So this picture here kind of shows you the partial sums with how your numbers go back and forth, and they will converge at some sum. And I'm going to come back to this picture later when we talk about actually estimating where that sum is going to be at. So we're going to call this the AST, and let's look at an example. Does the alternating harmonic series converge or diverge? Well, if it was just the plain old harmonic series, we know it diverges. So we list out some terms to get an idea of what's going on. This is my basic b sub n. We're going to go take the limit of that. Well, that's going to approach 0 when we take the limit as n goes to infinity. So that satisfies number 1. Now, let's see if it's decreasing. We put in n plus 1 for all your n's, and we cross multiply. Yes, n is less than or equal to n plus 1. If you want to subtract the n's and make it 0 is less than or equal to 1, fine. So both statements are true. So your original series, copy that over and say it converges by the alternating series test. Example 2, again, remove the -1 from the alternating series. We're just going to focus on e raised to the 2n power. That's my b sub n. We're going to take the limit of that. As this goes to infinity, wait a minute, that means my exponent is going to approach 0, and e to the 0 is 1. That does not equal 0. So therefore my divergence test comes into play. There's no need to do the second step. We just automatically say this series diverges by the divergence test. Example 3. Same situation. Do we converge or diverge? Look at just b sub n. Let's test the limit. All right, this limit goes to 0. We can prove that by taking and dividing by the largest n to the power to all your terms. So this is going to 0, this is going to 0, this is going to 2. So this becomes 0 over 2, which is 0. So 1 is satisfied. Number 2, let's show that it is decreasing. So I'm going to give you an example of how to do this by using the first derivative. You take the derivative, change your b sub n into a regular function, take its derivative by the quotient rule, and you end up with 3 minus 2x over 2 times the square root of x plus 2x plus 3 to the second power. See if this is going to be less than 0. Well, the only place we're going to be negative is the top, because everything on the bottom is positive right now. So 3 minus 2x is less than 0. Subtract over 3, divide by -2, flips the inequality. So yeah, we're decreasing as long as n is greater than 2. It doesn't matter when we start decreasing, as long as we decrease. We have decreasing terms as we go out to infinity. So both statements are true, and therefore our original series is convergent by the alternating series test. Number 4. Now you have the -3. So here's my negative. So we want to take that -1 out of our b sub n, if you will, because we want to remove that. So we want to look at just 3 to the n over n. Let's take its limit. Now, this one's going to be kind of tough, so I chose to put this in terms of x because I need to use L'Hopital's rule. Now, I guess you could leave the n's there. You still get the same kind of thing. It's just a habit of me that if I'm going to use a rule that works with just f of x, that I change everything back to x's. You don't have to, just my habit. So the derivative of the top is 3 to the x power times the natural log of 3. Derivative of the bottom is 1. We can clearly see that this is heading to infinity. It's not equal to 0. No need to do step 2. This thing diverges. So again, we'll take the series diverges by the divergence test. Example 5. Oh, where's my -1 to a power? That has something to do with the cosine. So if we look at cosine, because we know cosine goes from -1 to 1 for its range. So look what happens when n is 1. We'll be doing the cosine of pi, which is -1. When n is 2, we'll be doing the cosine of 2 pi, which is +1. Cosine of there's my alternating sign. So what we'll do is we're going to remove the cosine of n pi, and that's going to be my -1. And since we want a -1 on the very first term, I'm going to raise it to the power of n times n over 2 to the n power. There's my b sub n. Let's do its limit. Well, again, I have n's top and bottom. I'm going to use L'Hopital's rule. Now I have 1 over 2 to the x times natural log of 2. Now this approaches 0. So that's satisfied. Now let's show that we're decreasing. So here I'm just going to use the decreasing rule by putting an n plus 1 in for all my n's. So when I cross multiply this, or multiply this by 2, I guess is another way to do it, to get your n plus 1's the same on your powers of 2. You could cross multiply it and still have it work out the same way. I'll have n plus 1 is less than or equal to 2n. Both statements are true. So this does converge by the alternating series test. Our next example, well, let's see. Cross this off. This is going to have a limit of 0. Yep, I can see this already. I'm starting to get the routine down. Take the limit of b sub n. All right, now I got to show that it's decreasing. Again, a lot of n's. Again, you could use that same technique. I'm going to opt to use the derivative of the quotient rule. So here's my quotient rule. I simplify that. I get 2 to the x, 2x to the 4th plus 8x minus 3x to the 4th. Combine like terms. Look at the numerator. Make sure it's less than 0. The only thing that's going to be a problem is the 8 minus x to the 3rd power. So I solve that and I get x is greater than 2. So yes, this will be decreasing once I get past 2 for my n's, and then I have decreasing terms. Both statements are true, so yes, it converges. Again, you could have done this by putting in n plus 1 squared, n plus 1 cubed, and seeing if it's less than n squared over n cubed plus 4. I just didn't feel like foiling all that stuff out. So sometimes that first derivative test will go a little quicker if you know that just focusing on the numerator and set that less than 0. All right, our estimation of sums. Now this is where we're going to come back to this picture here. The alternating series estimation theorem says that if you add up all your terms of the sequence, and again, your b sub n has to be greater than 0. Everything is the same in the alternating series tests right to this very end, and then it says then r sub n. This is kind of like saying this is the remainder, the difference between the sum and the partial sum is equal to this, and that's less than or equal to what we call the first neglected term that's not in s sub n. So it's the very next term. So a better visual of this is to look over here at my number line. So I start at 0, I add b sub 1, I subtract b sub 2, I add b sub 3, and so on and so forth. But look at your partial sums down here. So let's say we're looking at s sub 5. Okay, there's s sub 5. If I subtract that from the s, that's this distance from this s to s sub 5. Well, that distance has to be less than the next term after b sub 5, which is b sub 6. This distance is greater than the difference of the sum minus the partial sum. If I went back, so from here I would add on b sub 7, which would probably be somewhere around here. That distance is greater than the distance between s and s sub 6. Okay, that's what this is saying. So the partial sum s sub n can be a useful approximation for the sum of the series. The error involved is this absolute value of r sub n. All right, so this creates a compound inequality. Your error, b, that neglected term, b sub n plus 1, we make it positive on the right, negative on the left. You have to be somewhere in between there. And then if you add the partial sum, S sub n, to both outsides, you create a potential interval for your answer for the sum. Whoops, I don't know where this arrow came from. So here's b sub n equals 1 over n times 5 to the n power. So that's removing this. I'm going to find my first few terms here until I find a value that is less than 0.001. Oh, that's what the arrow's for. It's for this term here. So when I get to b sub 5, this is less than my error. So I need to add the first 4 terms. So S sub 4 is negative. Now I go back to this series. Negative 1/5 plus 1 over 50 minus 1 over 375 plus 1 over 2,500 gives me this fraction or that decimal. So if I wanted to actually find S as an interval of possible answers, I take S sub 4 minus B sub 5, that's this value down here, the very last one we found, and then I add S sub 4 plus B sub 5. So writing in your numbers, crunching them out, my sum is somewhere between negative 0.1823306 and negative 1.822026. So I am really close. I am within 3 decimal places of knowing what that sum is. It's somewhere between the 2 and the 3 of that 4th decimal place value. All right, remember the rule that the error is using is S sub n to approximate S is smaller than the first neglected term. In general, valid for alternating series, that this satisfies the conditions of alternating series estimation theorems only. This rule does not apply to other series. I'm sorry I bleeped that out.